Welcome back to Multigrid Methods. Today, we're stuck in Chapter 7, Cell-Centered Finite Difference Methods and the multigrid solvers that are applicable for those. But at least we're in slide deck 3 of 3, so we're making good progress towards the light at the end of the tunnel. We talked last time about this variable diffusivity case, and we also started talking about cell-centered multigrid in 2 dimensions. I figured it's reasonable for us to spend a bit more time talking about this topic. It's a little more complicated than what we've done before. We've done some one-dimensional stuff. And yeah, so some of it we've already done, but let's take our time and go back through it. There's no rush here. And we'll pay attention to the details. Maybe spend a little bit more time doing some derivation. Now, somewhere in the middle here, we are going to get into some fairly complicated calculations. But I think if we take our time and break this down, I think things will make some sense to you. So the problem that we want to focus on in this section is the analog of what we've been dealing with in the one-dimensional case. I'm going to break this section down into 2 subsections. The one subsection is going to be on the constant diffusivity case. And so this will be the analog to what we talked about in the one-dimensional case. And then we'll go into the variable diffusivity case, which is the analog of what we just covered over here, but in 2 dimensions. Let me give a fairly general description of the problem that we want to solve, and then we'll specialize at first. So the problem we want to solve is this one. This is the non-constant diffusivity, or the general Poisson problem, in 2 space dimensions. But we're going to focus on, for simplicity, this square domain, omega 0, 1 cross 0, 1. Why are we focusing on a square? Well, we can do rectangles with the finite difference method. We can even do things which are non-rectangular, but then we have to do complicated stuff at the boundaries. It's not as simple in some sense as the finite element method for complicated shapes. The finite difference method can be done for complicated domains, but it's not so simple. But if you are on a square domain, and a lot of things are posed on square domains, for example, well, yeah, what is a good example? I'm trying to think. So in reality, a lot of geometries are not necessarily squares. That's true. And so it is a bit of an idealization to say that we're working in a square domain, but a lot of processes can be simplified to shapes which are at least rectangular, for example. So I'm thinking about materials where there might be some sort of phase transformation going on. We really don't care what's happening at the boundaries so much. What's really of interest to us is what's happening in what's called the bulk regions. And so in that case, it's okay to use rectangular or square domains. It's not so important. It's a little bit different if you're trying to solve the flow field in a river or in the ocean. In that case, it's a bit more important to know what the geometry is and how the boundaries affect the fields. But there are a lot of problems where the boundaries aren't so important, or the shape of the boundary isn't so important. And that's kind of where we're going to live for a little bit. The problem, as I said, that we want to solve is this problem. And this is kind of like a generalized Laplace operator. So you can see it's a second derivative. It's the divergence of something which looks like a gradient. Oftentimes we'll call this object here the flux. So it's a divergence of the flux is equal to some field. for example, maybe we're solving, so in this case, I'm calling this constant here the diffusivity constant or the diffusion coefficient. And again, I'm going to screw this up a lot. I know that already. This is not a constant, it's a coefficient. But for some reason, my brain just doesn't like to say the word coefficient a lot. But in any case, I'm going to call this the diffusion coefficient, even though this is much more general than what we call diffusion problems. I should say a little bit about why it's called a diffusion constant. Well, diffusion, you may recall, is a process which satisfies an equation like this. So time derivative of u equals divergence of some diffusion coefficient gradient u plus f. All right, so this would be a kind of diffusion equation where we have f being a source term. Okay, f is a source term. But now, how does this equation result from this equation? Well, I can think about this equation here, or this problem, as resulting from the what's called the equilibrium or the steady state of this problem here. And by the way, this problem should also be combined with some boundary conditions and also initial conditions. But if we're only interested in what's called the steady state, then at steady state, the time derivative of the field u is equal to 0. So this guy goes away. And then you can see the steady state solution for this time-dependent equation satisfies this time-independent equation over here that we call the Poisson equation. Now, in the context of the diffusion of particles, this d is a diffusion coefficient or a diffusivity. And so that's why I'm calling it a diffusion coefficient or a diffusivity, even though there are plenty of other places where equations like this come up, like, for example, electrostatics. In that case, this is a coefficient related to some electrostatic properties, and this might be the charge distribution. So this would be the potential, the electrostatic potential. This would be some coefficient describing electrical properties of material, and this would be the charge distribution, for example. And so in that case, this was not a diffusivity, but it's obviously has the same structure of equation. So I'm just going to call all coefficients like this a diffusion coefficient or a diffusivity. Now, the question is, well, how do we solve an equation like this? Well, you have various options at your fingertips. We know we have the finite element method. We could even hope that we could solve this analytically. So we have finite element. If we can't, we might have what's called a spectral method. But we also have this thing called the finite difference method, and that's where we're going to focus on in this chapter. And I'm going to break this into two cases, as we've already discussed. The first case might be whenever d is a constant. That is, it's not changing. It's just some fixed value. You might as well say d is everywhere equal to 1. So in that case, then this just becomes a Laplacian, and this is just the constant coefficient Poisson problem. Now, otherwise, we're going to assume that d satisfies this condition. Let's suppose that d is a continuous function over the closed boundary, or the closed domain, or the closure of the domain. And it's going to be a C1 function over the open set omega. And otherwise, it's going to satisfy this, this inequality. We just need to know it's bounded below by something which is positive and bounded above by something which is positive. And if we know that, then we know that this problem has a unique solution for every f, which is at least a continuous function. Actually, we can even do better, because we could say, well, f could be an L2 function over this open set omega and still expect to have a solution to this problem, but maybe in a weak sense. So this is the two-dimensional problem that we want to solve. Again, this is a review. So what I want to do is generate some spatial grid for the domain. Remember, the domain is a square, so I can take the same number of points, and might as well take the same number of points or grid cells in one direction as I'm going to take in the other direction. And so I'm going to just make the mesh spacing in the X direction and the Y direction the same because that's the simplest thing to do. And we're going to call the mesh spacing HL as we did in the one-dimensional case. Now, we're guaranteed to have the same mesh spacing in both directions if we choose a number of cells in each direction, X and Y, to be the same. And so I'm going to do that. I'm going to choose them to be equal to ML in number, where ML is equal to Q times 2 to the L, where Q is just some fixed positive integer. Well, the picture of this is something which looks like this. So if I have this domain 0 to 1, and I put 4 grid cells in the X direction and 4 grid cells in the Y direction, then I see that I'm going to have 16 grid cells covering the whole domain. So as I've shown here. Now I haven't explained yet what these points are, but well, at least I did last time, but I haven't said it again. These are my cell-centered points, obviously. I could choose, however, to use unknowns at these points, and these would be called vertex points. Now, it turns out there's a whole family of points that you might be interested in this cell-centered finite difference setting whenever you choose a grid like this. So I've already pointed out 2 of those to you. One is the cell-centered point set, which is here. The other one is the vertex-centered point set, which is here. Okay, and of course we have some boundary points as well, points on the boundary, etc. Right? So that one's open cell. Now, by the way, you might remember that whenever I did the regular finite difference setting, or the finite difference method applied on a grid which looks like this, I didn't actually need in 2 dimensions. I didn't actually need a degree of freedom here, 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 or here. So it's just not required to make the method work. And we're going to see what this looks like in the cell-centered context as well. So if I take 4 grid cells in the X direction and 4 grid cells in the Y direction, I get some grid which looks like this. But if I take 8 in one direction and 8 in the other direction, I get a grid which looks like this, or a mesh, whatever you want to call it, with 64 cells in this case. So this is the case where L is equal to 2, L equals 3, if I choose what for my value for Q? I think this should be Q equals 1, right? So if I choose Q equals 1, ML, that's the number of grid points in the X direction and Y direction. And let's just make this M2. So this should be 1 times 2 to the L power, which is 2. That's going to be 4. So, right, so this is L equals 2 and L equals 3 whenever Q is equal to 1. Right, so this is M3 equals 8. That follows the same pattern, 1 times 2 to the third power, which is to say 8. And I can keep going. I can keep making a finer and finer mesh to cover this 2-dimensional square, right? I mean, I can go and cover it with as fine a mesh as I please to have, as I want to have. So, as in the one-dimensional case, I need to define these things called the cell-centered points, and so the cell-centered points are precisely going to be the coordinates in blue here. And so to get the coordinates precisely at those blue points, you have to it's a bit like constructing the grid points for these vertices, right? But I have to shift things around a little bit. For example, this guy here, how would I describe what is the location of that point? Well, it requires these objects, these zeta points. So for example, For a generic L and a generic K, I'm going to define this thing called zeta LK to be K minus a half times HL. So this is the grid spacing at level L. And the reason for the subtraction of the half is because I really want to move those points from these vertex points into the cell center point. So that means I have to back off by a half. And of course, this is exactly the same procedure that I've done in the one-dimensional case. It's just that I have to do this um, both for the x coordinate and the y coordinate now. So, but the framework or the form of the points in both the x and the y direction are exactly the same. So that's why I'm not defining it differently in the x direction and the y direction. I'm just going to call it zeta LK. I don't have to prepend I don't have to call it x or y or whatever. So the cell-centered grid points are precisely the points that satisfy this formulation, right? So this is going to be the x cell-centered point, or the x coordinate of the cell-centered point, and the y coordinate of the cell-centered points. Now, these cell-centered points are defined for all I and j between 0 and ml plus 1. So, in fact, I could make them for minus infinity to infinity. I don't have to just limit myself to 0 and up to ml plus 1. But what 0 means is that's kind of the ghost cell. So that's these points out here, right? For the x with respect to the x coordinate. For the y coordinate, it's these guys. And then when I go above ml, that means I'm going to these points here, all the way up. So what I'm saying is the x points, I'm counting all of these guys, and y points well, x points in this direction, all of these guys. That's my definition. So there's 4 points actually that I've gotten in my definition of cell center points, which I'm not showing here, and those are what I call the corner points. So there's these extra points, 1, 2, 3, and 4, which I'm going to end up throwing away. Okay, so these are the excluded corner points that I'm not going to need for my method to work. I'm eventually going to throw those away. But for now, when I define these points, I'm including them in the definition by saying, well, I'm allowing I and j to both simultaneously be 0. And if I and j are simultaneously 0, then that's that point right there. If I and j are simultaneously ml plus 1, then that's that point, for example. Okay, but that's generically how I define these things called the cell-centered grid points. The set of all cell-centered grid points of kind of interest that I want to look at are all the grid points that I just defined, except I'm going to exclude those corner grid points. So these are the 4 excluded grid points that I talked about here, 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 and here. All right, so no matter what level of grid you're at, you're always going to be excluding 4 of those points. Now remember what we called these points which sit outside the domain of interest. Those are called ghost cells. So what I'm saying is I really don't need ghost cells at these 4 points. Okay, and these 4 points, those ghost cells can be thrown away. I just don't need them. They're not important for my approximations. So that's why these excluded things are excluded. I'm not going to need them. So the grid points that don't belong to this omega, as I said, are called the ghost points. We'll often also be interested in just narrowing our focus a little bit and looking at the set of cell center points which are only in the interior of the domain. Those are what I call the interior cell-centered grid points, and those have a special name or a special notation. I'm going to put this superscripted circ on the CL set. So this means only those cell-centered grid points which are in the interior. Okay, so remember this domain is an open set. If I take CL intersected with that set, then this open set, then the points I'm going to get are precisely these filled blue points. So the filled blue points here are my interior grid points, my interior cell center grid points. And these outside of here okay, that are still in this set are what are called the ghost cells. Okay, the ones that, except for the excluded ones, those are also kind of ghost cells, but those are the ones that aren't inside of omega. Okay, so cell-centered grid points of interest, and then the interior cell-centered grid points. That's the notation for those two sets. And then I'm also going to be interested in what are called grid cells. We talked about this last time as well. The grid cells are just these sets here. Okay, so there's a grid cell, there's another grid cell. And I've done this so that they're all disjoint. I've defined them so that they're disjoint. And so if I take the union of all of those guys, what do I get? Well, if I take the union over all I and j, I suppose I should say I and j equals 1 to ml. If I take the union of those sets k, l, I, j, then of course I'm going to get the set 0, 1 squared. Or in other words, 0, 1 half open interval product with itself. Cross product, right? Right, or not cross product, but this set. All right, so that's just so that they're disjoint. Sometimes that's a useful thing to have. So those are the grid cells, right? The grid cells for this this grid are a lot smaller, right? They're a quarter of the area of these grid cells, right? So you can see each one of these grid cells kind of stays in the grid that I've just created, but they get subdivided into 4 daughter cells, child cells. Okay, what else should I say here? That's about it. Now, as in the one-dimensional case, we have a bunch of these function spaces that we can define. For example, we can define the space of piecewise constant functions, the VL spaces. And so these are functions that go from this half-open square into R, such that when I restrict V to each cell, they're just constant functions. So these are, of course, piecewise constant functions. Now, this wouldn't be a good enough space to use if I was interested in the finite element setting, the conforming finite element setting, because such functions are not, well, I should say it like this. This function space is not a proper subset of H01 omega, right? It's not a subset. Unlike the finite element spaces, which I took some care to formulate previously. So, of course, we've already seen this in the one-dimensional case. Just wanted to emphasize that it's still true in the two-dimensional case. And now we have 2 classes of functions, or I should actually say 3, that we're interested in the finite difference context. So in the finite difference context, we're just thinking about grid functions, unlike functions over this functions of this type. We're thinking about grid functions which take the points in our cell-centered mesh, if you want to call it that, and assign to those points values, right? Real values. So this functions here are defined for all the interior cell-centered grid points and the ghost cells as well, except just keep in mind we're excluding these 4. We don't need those 4. So we're defining functions, or we're imagining functions where for each one of these interior grid points, there's a value defined at that point. And for each one of the ghost cells, there's also a value defined at that point. So, by the way, what would be the number of degrees of freedom, for example, in a function on a grid which looks like this? Let me get rid of these points here so that there. Okay, so what would be the number of degrees of freedom? Well, I have 16 interior degrees of freedom, and plus another 16 exterior degrees of freedom, or ghost cell degrees of freedom, for a total of 32. That's a little bit weird because are exactly the same number of degrees of freedom in the interior part of the grid as there are on the ghost cells. This doesn't hold up for very long because as I make my mesh finer and finer, the number of ghost degrees of freedom starts to become much smaller than the number of interior. So for example, here there are 64 interior degrees of freedom for such functions, right? So all of these filled blue dots, and then plus another 4 times 8 or 32 exterior degrees of freedom. So there's a whole lot more interior degrees of freedom than there are exterior. And as ML gets larger and larger, um, it becomes a whole lot more interior grid points. So that's that function set or class of functions called the cell-centered grid functions. We're also usually interested in cell-centered grid functions, or the sets of them, defined only on the interior degrees of freedom, or only on the interior cell-centered grid points. And so we call those interior grid, cell-centered grid functions. Interior cell-centered grid functions, okay? These have fewer degrees of freedom than well, I should say functions in this set have fewer degrees of freedom than they do over here. These are, by the way, functions, and if I add two functions from that class together, then I get a new function. I can subtract them. I can make linear combinations of them in the usual way that I make linear combinations using functions. And so, in fact, this is a function space, and this is a function space, and I can ask what's the dimensions of this function space? The answer is, for this one, it's easy to say. This one, the dimension of this function space is just the number of interior cell-centered grid points. And this one, the dimension of this space is just the number of cell-centered grid points. That's the dimension of those respective spaces. It's also going to be important to define what are called the homogeneous Dirichlet cell-centered grid functions. And we talked about this last time. So the importance here is that we really need to think about, well, the first thing you want to think about is when I make a grid, and I'm using degrees of freedom that are located at these points, these interior points, how in the world can I set the values of a function equal to 0 on the boundaries? Well, the answer is you can't. You don't have a degree of freedom which lies exactly on the boundary. The way around this is to use what are called our ghost cells, and then to use what's called an average, right? An average which gets us back to, well, an average which can be interpreted as lying on the boundary. So for example, if I have a ghost cell out here, let's just look at a couple of these. Let's say I have these 4 ghost cells to consider, right? So what I'm going to do, and of course I've got ghost cells going up this way as well, just to complete the picture a little bit. And I'm not drawing the other ghost cells. Well, the idea here is, if I want to set homogeneous Dirichlet boundary conditions, I'm thinking about a function which has degrees of freedom at this point and that point, and which is 0 at that point. How can I do this? Well, what I'm going to say is that I can't force the function to be 0 at that point, but I can force its average to be 0 at that point if I interpret the average in the right way. So what I'm going to do is take the average of a function which has degrees of freedom at those 2 points. The average works out to be a second order approximation of the true function at this point here, this boundary point. Okay, it's a second order approximation. Same thing is true here. The average of a function in this direction at this point, right, from degrees of freedom at these 2 points, is a second order approximation of the true thing. So you can use Taylor's Taylor expansions to prove that to yourself. So I can't demand that the function is precisely zero at the boundary, but I can demand that its average is zero. So that's exactly what's happening with these cell-centered grid functions. I'm demanding that there's function or that their averages, which I can interpret as landing on the boundary, are zero using these ghost cells. Okay, and so you notice that I don't need a ghost cell here to make that happen. Well, this gives me a bunch of conditions. How many conditions does it give me? Well, it gives me 4 in this direction for this example, 4 in this direction, and even though I didn't fill it in, 4 in this direction, 4 more here, right? So 16 total, 16 total equations, each of which has the practical effect of eliminating the degree of freedom at the ghost cell. Because if I tell you what the value is in here, these interior points, and then I demand that the average is zero on the boundary, then that eliminates the ghost values or the values at the ghost cells as degrees of freedom. So I'm going to define this set of functions called the homogeneous Dirichlet cell-centered grid function set, subspace, I guess, of the previous function class that I had defined, where the boundary averages are zero. So this requires some interpretation or definition, this notation, because as I said, I can't have a grid function which is precisely zero on the boundary. It doesn't make any sense. And what I'm interpreting this to mean is that those 4 average, well, not 4 exactly 4, but the averages on all 4 boundaries, okay, counted at every boundary point or every grid cell, are all zero, right? So this is the one, these are the averages whenever I is equal to 0 or 1. So that's along here. And whenever j is equal to, see, 0 or 1, then that's the average along here. So this guy is that one. This guy is that one. So let's draw those on here, maybe using a purple crayon. So this one is that boundary. This guy is that boundary. Where is this one? This is that boundary. And this one here is that boundary. Okay, so I have 4 different conditions kind of demanding that these averages are zero on the boundary. As I said, that eliminates as degrees of freedom the ghost cells. And so I'm really restricting how many degrees of freedom functions in this subspace have. All right. Now, if I have a function that satisfies these conditions, then we say that the discrete homogeneous Dirichlet boundary conditions hold, even though its values at the boundary aren't exactly precise. And of course, we're going to write this for those words. And 6 is, of course, the sets of equations that we need to hold at some level L. Okay, so these are my 4 equations or 4 sets of equations that describe the discrete homogeneous Dirichlet boundary conditions. Right. What else do we have? I think that's about it for that. Okay, so this is also something we talked about last time, but I wanted to emphasize again with a bit of discussion. So we have this way, especially if I view functions from this function set or this function class, this way of reinterpreting these grid functions as a vector of a certain length. And the way I do it is pretty simple. I take a grid function, which is defined on a grid, of course, cell-centered grid. This one is going to have exactly 16 degrees of freedom if it's an interior cell-centered grid function. And the question is, what's a canonical or standard way of interpreting these degrees of freedom into a vector? Well, what I do is I'm going to create a, long vector. I'm going to create a 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 long vector. I'm going to Okay, with it has to have 16 elements in it, right? So that's clear. But I'm going to take them in various ways. So for example, the green ones are going, the 4 green degrees of freedom are going to go first. I did that wrong, right? That's one way of doing it, but actually this is the way I want to do it. Those green ones will go first. Let's take these 4 blue ones next. And the way I'm counting these guys is I'm going left to right. Okay, so it's, and these next 4 go here. And I don't know if you'll be able to see. Let's see, what color do I want to use next? Let's use orange. The 4 orange guys go next. And then finally, oh, what do we want to do next? Red. Those guys go here. Right? So that's how I map the grid functions into vectors. And of course, I can go the other way around as well. If you give me a vector with 16 elements in it, I can immediately create a grid function that has 16 degrees of freedom. I mean, that shows you right away that the dimension of this space, if you couldn't see it already, for functions in this space, has exactly is exactly the same as the dimension of objects in this space with vectors of length ml squared. So the dimension of the space is ml squared. So the precise way of stretching this grid function out into a long vector is given by this formula. So this is the vector that I want to create from this grid function. And so, for example, the first thing I'm going to do is set j equals to 1. Okay, j equals 1 is going to be this row. So j equals 1, this guy goes away. And if I index I from 1 to 4, that means I'm filling these 4 elements. Now let's set j equals to 2. So that'll give us that row. J equals 2 means j minus 1 is 1. So this is going to be I plus ml. So that's 5 in this case for I equals 1. Then 6, 7, 8. 5, 6, 7, 8. Okay, and then 9, 10, 11, 12, 13, 14, 15, and 16 for this last row. And the last row is given to me by j equals 4. So the way I can think about it is indexing I in this direction and j in this direction, which is exactly how I normally count or index my grid functions to begin with, right? So, well, I mean that's kind of self-evident from the notation that we used previously. All right, so let's so to keep the notation that we've had previously, we always called our number of degrees of freedom NL. And I want to keep up that practice. So NL should be ML squared because there's ML degrees of freedom in this direction, ML degrees of freedom in that direction. The total number of degrees of freedom is ML squared. And therefore, the total number of degrees of freedom I want is NL equals ML squared. This shows clearly and right away that the dimension of this function space is ML squared. But now I can always go back, right? I can, for every function in this space, I can define a function in this space and vice versa. This is the space of homogeneous Dirichlet cell-centered grid functions. How can I do that? Well, once I know that a function is here, I can create ghost cells for that value. So for example, I can take a ghost cell and just create it as a degree of freedom. And I know that the value is going to be over here is going to be minus the value there. And for example, the value here is going to be minus the value there because I'm just going to create degrees of freedom at the ghost cells so that this holds. But that's not really adding any new degrees of freedom at all, right? Because those values are completely fixed, completely determined by the values along the boundary, right? So for example, the boundary values here determine the ghost cell values here. These guys determine them there. This one determines them here. And the values here determine the values of the ghost cells here, right? So you should be able to see right away that the number of degrees of freedom in a function in this space is the same as in this space. So I can get a one-to-one mapping of functions from here to here, one-to-one onto mapping. What about this space? Well, that one's also easy, right? These are piecewise constant functions, and piecewise constant functions can just be computed in the or generated in the usual way. I think we talked about this also last time. So if I have a grid, let's make it easy. So there's a grid having 4 cells, right? So maybe this is, what do I want here? So usually it's going to be I in that direction and J in that direction, okay? Or in other words, X and Y. So if I have a grid function that's defined at these 4 grid points, that means I have a value, for example, at this point. And the way I'm going to create a piecewise constant function is I'm just going to make the value on that whole square equal to the value at the cell center point. So for example, I'm going to make a function. Let's see. Right, so its value, I kind of drew that a little off center. The value at the cell center grid point just becomes its value over the entire square. So it should be fairly easy for you to see how you define a piecewise constant function from VL from any grid function you want to define. So the dimension of all 3 of these spaces is exactly the same. It's NL. All right, now I think this is basically on to some new stuff. So the first case that we want to consider is whenever D is equal to 1. So the idea is if D is equal to 1, then my operator that I want to approximate is this operator here. That's just minus the Laplacian operator. Now you might ask yourself, why do mathematicians always put minus sign in front of that? It's because the positive version of the operator is the minus operator, it turns out. If I leave it off, then it's what we call a negative operator, not a positive operator, negative linear operator. It's the analog would be a stiffness matrix, which is negative definite instead of positive definite. Now, negative definite and positive definite, they differ only by that sign. And if you know you have a negative definite matrix, it's as good as knowing you have a positive definite one. Okay, so in any case, we need an approximation of this operator. And what we're going to do is just use the usual 5-point stencil. I'm going to talk a little bit more and generalize how you get a hold of this 5-point stencil in more detail when we get to the non-constant diffusion case. Right now we're talking about the constant diffusivity case, and specifically D equals 1 because that's the easiest one to deal with. But you've seen the derivation of this from the basic numerical analysis classes in the non-constant or the constant diffusivity case. So the only one I really want to spend much time on is the non-constant case in a few slides hence. So, well, we want to approximate our PDE using this as a replacement for this operator. Okay, that makes sense, right? But again, what are we going to do for the boundary values, the boundary conditions, right? We can't really enforce them point-wise. Well, what we're going to do is just demand that we have those averages being equal to 0, right? So way I'm going to define this then is I'm going to say, well, okay, if I have a function that has these homogeneous Dirichlet boundary conditions. What did I call them previously? Discrete homogeneous Dirichlet boundary conditions. Well, that means that what I'm doing with that function is eliminating the degrees of freedom at all the ghost cells. okay? And the reason I want to do that is because functions in this class approximate pretty well functions that are continuous that have their values being 0 on the boundary. So that's where I want to start with. That's what I want to start with. These grid functions that have their averages being 0 on the boundary. So I can, obviously for those, I can approximate the second derivative of those functions with this um, this this discrete or this finite difference minus Laplacian operator. So sometimes we call this the discrete Laplacian operator. Discrete Laplacian. Or it should say in this case, discrete minus Laplacian. Okay, discrete minus Laplacian operator. So it's going to act on grid functions. So grid functions that are defined at interior points and at our ghost cells. And remember, we don't need the 4 corner ghost cells. We've thrown those away already. So this can be thought of in terms of pretty standardly in terms of what is called a stencil. So you most of you have seen, or I've referred to stencils before. Some of you may have not seen this before. And all this means is a stencil just says what points are you going to use, and then what coefficients for the points or the values at those points are you going to need. So as I said, we're going to define this Laplacian operator at all the interior points. Okay. Now, interior points, that usually means that my indices are between 1 and ML. And here they are. The indices I and j are between 1 and ML. So that's where I'm going to define these values. I'm also going to need values at my ghost cells, but I can't actually define the Laplacian operator at those points, but I need them to calculate the points at some of these interior points. Here's the idea. So let's suppose I want to calculate the discrete minus Laplacian operator at that point in blue. What points do I need to do this? Well, I need to know the value of VL at this point, at that point, at that point, and at that point. Okay, so those 4 points, in addition to its value at the point where I want to calculate this. So I'm thinking about calculating these using nearby values and then have the approximation counting or being for this cell-centered point right there with the X on it. All right, so this is what I call a stencil. Now you see pretty clearly, if I want to calculate the Laplacian at this point, I'm going to need the values at 2 different ghost cells. I'm going to need the one here and here, in addition to these interior cells, and in addition to the value at the cell itself. What about at, say, this point? Okay, this point up here. Which ones am I going to need? I'm going to need this guy, so 1 ghost cell, and I'm going to need these 4 interior points. Okay, so you can see that's why I need values at certain ghost cells, right? Now, it just so happens that I'm going to define this operator for functions where the values of the ghost cells are determined by that discrete homogeneous boundary condition. So in other words, such that the average is equal to 0 there. Okay. Now that means actually I can, in my formula for this operator, minus the discrete Laplacian operator, I can eliminate the ghost cell in the formula. And I'll show you how to do this in a minute. Okay, so this is something I just mentioned, right? So the grid operator can be expressed as a stencil. And this is actually the notation we use for a stencil, right? So I did forget to say one thing, right? In the definition of this operator, I'm dividing by HL squared. And so that's where that's coming from. And then these coefficients here, -1, -1, -1, -1, and 4, those are precisely these coefficients here. 4, -1, -1, -1, and -1. And if you look at this, this precisely maps out this pattern that I showed you here. So that's why I'm using exactly the same pattern here. It's kind of like a so there used to be this this game, what was it called? Maybe it was called Jacks or something like that, which had one of its pieces which looks like this. It kind of reminds me of that. In any case, this is the shape of the stencil, and the coefficients are precisely the coefficients that I use in my expansion. Now, I can eliminate, as I said, when I get near a boundary, I can eliminate these guys as degrees of freedom, and that modifies my stencil. Let me show you how this works. Well, I'll show you over here. But before I get there, let's explain our cell-centered finite difference approximation. So remember, we're approximating minus Laplacian of u equals f in omega, and u equals 0 on the boundary. Okay, so how am I going to do this? First of all, as I said, we need to sample f at the interior cell-centered grid points. So that's very easy. I just create this new grid function called FL, where it's the values of this grid function are just the values of f, but localized to the cell-centered grid points. And then the problem is going to be the cell-centered finite difference approximation is just find a grid function from this space, which has those homogeneous Dirichlet boundary conditions attached to it already, that satisfies this approximation at every interior grid point. All right, so the homogeneous Dirichlet boundary conditions are enforced in the definition of the space. Okay, the homogeneous Dirichlet boundary conditions are enforced in the space, but those boundary conditions are precisely defined in equation 6, or the multi-line equation 6. So that's if I build the boundary conditions into the space. I don't have to worry about the fact that this changes. Okay, if the boundary conditions are built into the space of solutions. So I hope everyone gets that concept. Boundary conditions are built into the space. I have an alternative, though. I could build the boundary conditions into the operator directly, right? And so that's what's happening here when I define this thing called the interior minus discrete Laplacian operator. So this guy has, I've got a typo here, right? Because this guy is defined for functions that are interior only. Okay, so I think I might have, this one should have also just been interior. Okay, so this one has ghost cells that are defined via my homogeneous Dirichlet boundary conditions. But this guy is, once I calculate the discrete Laplacian, it's only got values at these interior points. So that creates a new interior cell-centered grid function. Okay, so this distinction is important, and I screwed it up. But I'll correct that in the notes. So what I want to do is I want to define a new interior minus Laplacian operator that only acts on functions that have values at the interiors. And of course, I already know that it's going to send me to values that are to functions that have values only at the interiors. So how does this work? Well, for example, if I'm at the left boundary, there's nothing outside of here, right? Well, I can think about eliminating that as a degree of freedom so that there's nothing outside of there. That's kind of the more proper way to put it. So let's think about how I would define this. Let's go to a new page. Okay. So where did this stencil come from? So that's what I want to explain right now. Well, we're working near the left boundary. It suffices for me to create a grid like that. So for example, I want to calculate the Laplacian at that point. I know I'm going to have to use a stencil that has these 4 points, right? But now I want to eliminate this ghost cell as a degree of freedom here. So how do I do this? All right, so this is going to be I equals 1 and j is equal to 2, right? So I want to calculate minus u l 1 2. What's the formula for this? And let's assume that we're going to start with ul being a grid function in CL0. So this means a grid function which has homogeneous homogeneous Dirichlet boundary conditions. If I said Neumann before, I apologize. Homogeneous discrete Dirichlet boundary conditions. Right. So I'm gonna use my stencil as usual. So it's going to be minus u. Let's see, which one did I do first in my definition? I'm going to do I plus 1, I minus 1, j plus 1, j minus 1. Okay. Just want to stay consistent. Okay, so I plus 1 in this case is going to be 2. And j we keep the same. I minus 1, well, I is equal to 1. So I minus 1 is 0. And j doesn't change. Then we're going to add and subtract values onto j. So L, I is equal to 1. Then we're going to do j plus 1, which is going to be 3, minus UL1 j minus 1, which is going to be 1. So those correspond to that point and that point. And then finally, I'm going to do plus 4 UL 1 2. And I divide by HL squared, whatever that is. Right. Now, I know that I have the homogeneous Dirichlet boundary conditions holding at this boundary, right? In particular, I know the average at that point is 0. That involves the average of those 2 points. So I know that U L 0 2 is equal to minus U L 0. No, sorry, it's going to be 1 2. Now, what happened to the division by 2? Well, okay, so let's take this a little bit more slowly. So first of all, I'm saying that the average is equal to 0. But what does that mean? If the average is equal to 0, that simply means that UL0 2 is equal to minus UL1 2. So now I have my formula that I just wrote, still true. That's still my approximation at that boundary point, or near my boundary point. Why do I say near my boundary point? I'm not at the boundary point. I'm at a point which is adjacent to it, as close as you can be. So which one did I just replace? I got rid of this guy as a degree of freedom here. Right? I just eliminated him as a degree of freedom. And what I gain is I gain a net of plus UL12, right? Because I get minus a minus. So this becomes plus UL 1 2. But now that's just what I would call the diagonal element, okay, or the point at the center. So this guy can be, in other words, this term and this term can be combined, right? The 4 and the 1 can be combined to give what? Just a 5. So effectively, I'm saying that I eliminate that degree of freedom at the ghost cell, and I replace this with what's called a modified stencil. All right, so the stencil now has the coefficients minus and then nothing, and then minus, minus, and 5. Okay, and of course, everything always gets divided by HL squared. So what I have here is a modified stencil, which looks like one over HL squared. I'm going to have a 5 in the middle now. I still have minus 1s here and here. I could, I guess, put a 0 here, but the convention is when you have a 0 at a point, you just drop that from your stencil. It's the same reason why I don't have any coefficients here, here, and here. All right? So this is my new modified stencil near the boundary. That's precisely what I'm showing here. Whenever I'm near the left boundary, as long as I'm not at a corner point, that's how I modify my stencil. What do I do if I'm at one of those corner points? Well, for example, I'll get there in a minute. Yeah, let's say if let me not get ahead of myself. Okay, if we're at the left boundary, we modify the stencil like this. That makes sense, I hope. What about if I'm at the bottom boundary? Same considerations, right? Except now I'm down here, for example. And I want to eliminate this from my stencil by using my boundary condition. So same procedure. It's just that instead of eliminating this point, I'm going to eliminate this guy down here. That combines with the diagonal element, if you don't mind me calling it that, to give a 5. But it's entirely analogous. Okay? Right? So same deal. But what about if I'm at the one of the corner grid points? So for example, the easiest one to consider first is, what if I'm at that point and I want to calculate my discrete Laplacian approximation? Normally, I would want to use these 2 ghost cells and these 3 interior cells. But after I go through and eliminate the degrees of freedom from the ghost points, I'm going to get a +1 on the diagonal element for each one of these eliminations. So that's why the diagonal element, if you don't mind me calling it that, instead of being 4, goes up to 5 and then 6. So I add 2 degrees of freedom to that, or the coefficient changes from 4 up to 6 because I've eliminated this guy and this one, right? That makes sense, right? And so now if I look at this guy, what's the stencil going to be? It makes sense, right? It's just going to be, if I write out the stencil for the one here, and I'll leave off the other stuff. It's just going to be minus, well, I've got to at least make it legible, right? So it's going to be -1, 6, -1, and then zeros. So that's if I'm at that point there. And similarly for this point up here and this point here, or I should say analogously. You can eliminate the stencil or the degrees of freedom. What's this one going to look like? It's going to use those points. So the stencil is going to be 6 minus 1 minus 1, right? So that the stencil for that point looks like that. And I can keep going in this way. I can create a stencil for points up here, right? They're going to have 5 on the diagonal. Same here, 5 on the diagonal. Where the center point coefficient is going to be 5. The same considerations, right? So these are what I call modified stencils near the boundary. So what I've done is I've created an operator which doesn't need the values at the ghost points. So this I call the modified discrete Laplacian operator. I could write out the equations for it, right? I could write out all 16 equations for this guy, but I don't need to do that. You simply say, okay, well, the stencil is the same for any of the points in the far interior, but near the grid points, I have to modify the stencil in the ways I just mentioned. Okay, so and how many modifications do I have to make? Okay, well, the number of modifications has to do with how you classify points. In here, if I'm well into the interior, I don't have to modify the stencil at all. But I have to modify the stencil here. So that's one modification. Here, that's second modification. Here, and here. So there's 4 modifications for those groups of points. And then 4 modifications at each one of the boundary points. So I have to modify the stencil in 8 ways, right? And so that gives me a total of 9 different stencils that I have to use. So that's kind of annoying and a little bit cumbersome, but it's not hard to remember how you have to do these modifications. If I'm using like a loop, then I simply have to say I have to have these 9 different cases, right? I have to check the values of my indices and modify the stencil accordingly. Right. So now I have and again, previously I had a couple of typos that I have to go back and fix, but basically I've created 2 different operators, right? So this guy came first, and it was a way of I defined the operator so that there were absolutely no modifications at all. I used the fact that I had these homogeneous Dirichlet boundary conditions in the discrete sense, and I applied this this operator to those grid functions, and I produced an interior grid function, an interior self-centered grid function. This operator here means it means something slightly different from this one. It means what you're going to do is you're going to modify your stencil so that I don't need degrees of freedom at those ghost cells at all a priori. Okay, so it kind of like modify. So this one is the modification of the operator, okay, using the boundary conditions. And this one is the old operator or the standard operator where the boundary conditions are built into the space. All right, so I have now 2 different ways of describing exactly the same problem, which I hope you'll see are entirely equivalent. The first way I call the P superscript circ problem, and that is given a interior cell-centered grid function, you're going to look for an interior cell-centered grid function such that minus the interior discrete Laplace minus interior minus the discrete Laplacian acting on that interior cell-centered grid function is equal to an interior cell-centered grid function. It's a lot of words, but I hope you see that that is equivalent to what I defined earlier, which is what I'm going to call P sub 0. P sub 0 is the same. You're given f as an interior cell-centered grid function, and you're looking for a cell-centered grid function that's not necessarily an interior one, but it satisfies the homogeneous Dirichlet boundary condition satisfying this. So the question is, which one is easier to write down in code? Well, it turns out actually, if I'm going to write a code, it's much easier if I just say, okay, let's say I just want to apply this operator to a grid function. It turns out it's not so hard to do this if I simply say, okay, I have a grid function. I'm going to modify its values of the ghost cells so that it ensures that the homogeneous Dirichlet boundary conditions are satisfied. And then I deploy my operator without any modifications. That means I don't have to put any if conditions. And I can apply that directly, and it gives me on the output a cell-centered interior grid function. And I can check to see, is that guy equal to this cell-centered interior grid function? Okay, so that's not exactly how I would solve this problem, but everything makes sense. If I just want to apply this operator, it turns out in code, this one's quite a bit easier than this. Why then should I even define something which looks like this? So it's just for, well, I can say it like this. This one is more closely related to the stiffness matrix formulation. All right, so which is what I'm going to talk about next. The stiffness matrix, what is the stiffness matrix? Well, it turns out if I want, let's focus on this version of the problem here. How many degrees of freedom are in the solution of this problem? Well, as we said, NL, which is ML squared. Okay, we know that there are going to be exactly NL equations in NL unknowns here. So it's going to be linear, so I can turn any linear system of equations into a matrix set of equations. All I need to know how to do is a mapping of grid functions into coordinate vectors. But I already have that. I already have this, what we call the lexicographic mapping. I might have failed to call it that. I might have called it the canonical mapping, but it's actually called the lexicographic mapping. Lexicographic means that it's kind of what I call the typewriter mapping. It's the one, although it's a typewriter which types from the bottom of the page up. So it goes this way, and then it goes, right? That's called the lexicographic mapping. So it turns a grid function using this specification into a vector. That's all I need to know. And then I can translate my linear equations into a matrix problem. And it just so happens if I use that lexicographic mapping, that I can turn these NL equations and NL unknowns into this matrix problem. ALUL equals FL. Now, this AL is what we call the stiffness matrix, and the UL is the vector of unknowns, and the FL is what we call, generally speaking, the forcing function. The forcing function is gotten through the lexicographic mapping. I just take my grid function, FL, and it's an interior grid function, and I map it to its vector by the usual procedure, right? I stack the degrees of freedom like this, right, to produce a vector of length 16. So the question is, what does the stiffness matrix look like? The stiffness matrix is what we call a block tridiagonal matrix. All right, so where we're going to pick up next time is, what is this block tridiagonal matrix? What's its structure? Well, I'll answer those questions very briefly before we sign out. The structure of this block tridiagonal matrix is given here, where the blocks are these matrices here. Now, just like in the one-dimensional cell-centered case, I have to remember, in the cell-centered one-dimensional case, I had a weird thing happening here and here. And the same weird stuff is going to happen for these first block matrices. And so we'll discuss that next time, and we'll stop there.